Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we talked about the projection of vectors onto other vectors, and we talked about some of the properties of the projection. And in this video what I want to talk about is a vector product. So is there a notion in which we can multiply two vectors in Rn and then result in a new vector? So as hinted by the title here, in fact it cannot be done in general that I can take any two vectors in Rn, or I can take a notion of a multiplication in for any vectors in Rn or for any n in the naturals. In fact, I can only define a notion of the vector product, kind of a multiplication of two vectors, in R1, R2, R3, and R7. The reason that is true is related to something a bit deeper that we're not going to talk about in this course, which is how they're related to something called the norm division algebras, which is the real numbers, the complex numbers, the quaternions and the octonions. So that's the reason why we can only define it in that case. And it turns out actually the only non-trivial ones in which we can define multiplication are in R3 and R7. But the only one that we're going to talk about here, because it has a nice geometric meaning, is in R3, but it's important to emphasize here that, unlike addition that could be defined across kind of every different n in Rn, multiplication cannot be defined for every single n. It's very restrictive. So we call this thing the vector product. As you might expect, it's the product of two vectors. It takes two vectors and results in a new vector. It's sometimes also referred to in the literature as the cross product. So let's write down what the definition of this thing is, because you might have seen this before. And what it means geometrically. So we let u and v, as always, kind of be vectors now, but specifically in R3. Then we say, then the vector product or as I said, it's sometimes referred to as the scalar product, is defined as, we write it as u cross v, kind of like our usual multiplication symbol, is equal to the norm of u times the norm of v times by the sine of the angle between them times by some new vector n, and we'll talk about what that means in a minute. So let's just write this where theta is the angle between u and v, and n is an orthonormal vector to both u and v. That is the dot product. So let's maybe kind of make a note of this. That's to say that n dot u is equal to n dot v, which is equal to 0. And we also have that the norm of n is equal to 1 because it's an orthonormal vector, as I said in the previous video. So how do we interpret this? Well, this factor here in front is simply just a scale factor. So it's just going to be something that stretches our vector or shrinks it down. But the important piece is this thing here, right? So what it's telling us is that the cross product, or the vector product between our two vectors in R3, results in a new vector that is perpendicular or orthogonal to these two vectors. So in other words, if I'm given, I can think of these two vectors are going to lie in some plane in R3. So if I have some two vectors pointing out, they lie in a plane. And this vector here is the vector that is perpendicular to the surface of that plane. But what we immediately notice is that there's not a unique vector that I can define, right? Because if my plane, for example, was like my hand like this, I could define the normal vector to be the one that goes outwards like that, like my pen pointing in this direction, or I could pick the normal vector to be the one flipped round the other way in that direction. Which one do I pick? Which one is, does define this vector u cross v? Because it seems that I can have two results. I've got, two vectors going in, and I can have two choices of two vectors coming out, which doesn't really make much sense, because if we want to think of this as kind of like a function, as you've seen, it only leaves a unique value that it gets out. It can't spit out two values. And this leads us to this idea of an orientation. And it follows from the fact that the R3 is in fact has two different orientations, and these things are called the left-handed and right-handed orientations. And effectively what that means is if you take your left hand or right hand, like so or whatever, and if you imagine these two fingers as your vectors, your u and v that you're putting in, you pick this choice of n. So if I pick this orientation, that would mean that and these two vectors here lied in my plane. The normal vector that I would pick would be the one pointing upwards. But with the left-hand orientation, that would be the one that I would have the vectors pointing this way and my other vector pointing this way, and I would pick it so that n points upwards for this orientation. So when I just refer to the left-handed, right-handed orientation, it's just these two different orientations which define which whether or not the normal vector is pointing upwards or downwards for this orientation, right? Because if I put my left hand in the same orientation like so, you see that my thumb is pointing downwards. So they only differ by the fact that either my vector points one way or it points the negative of the other way, right? And generally what we're going to do is we're going to choose the right-handed orientation in this course because that's the convention that's generally done in most textbooks. And it's just the one that we're going to pick here. So how do we actually define the right-handed orientation? Can we define that explicitly in this situation? Well, we can define it by simply saying what the vector product is between some of our basis vectors that we defined in a previous video in R3. So we talked about these basis vectors I, j, and k. If we can just say what the direct result is of the vector product of I with j, I with k, and k with j, then that would tell us which orientation we're picking, and the one that we're going to kind of define is going to be the right-handed orientation. So let's write down that now. So we can say that the right-handed orientation is defined via the relations of the following. So we define these vector products. We take I, and when we cross it with j, that results in the vector k. So in other words, that's this one that we've got here, right? This is I, j, k is pointing upwards. The other one we take is j cross k is equal to I. And then the last one we need to consider is k cross I is equal to j. And it follows from our definition above, and just using the kind of phase difference of sign, of the sign factor in the cross product, that it follows that if we have the u cross v is clearly going to equal minus v cross u for all v and u in R3. So the other ones we can define using this relation here, and then we can simply just flip these round at the cost of a minus sign. Okay. And using the definition now, or definition of the cross product or the vector product, it follows that what happens when we take the norm of the cross product? Well, the norm of the cross product or vector product is simply going to be the norm of u times by the norm of v times by sine of theta. Because previously we had this term n here, but if we take the norm of n, because n was orthonormal, it equals 1. So the norm of this whole thing is equal to this. Why is that useful? Well, it turns out this thing here, the area spanned by a parallelogram constructed out of u and v. So what do I mean by that? Let's maybe draw a picture so you can see how this works. So let's write kind of our vector here. Think of this thing here as u, and we'll do kind of another vector, a green vector, we can do as a v. And then if we kind of take v up here as well, we write this as this is also v. And we also have our vector here, u, should really join up. Then in this region here in the middle, I'll kind of shade in blue, this A is equal to the norm of the vector product of u and v. And this is effectively seen, or this can be constructed via Lagrange's identity, which is where we're going to prove this. And That's where we're going to finish off. So using the cross product, we can actually find the area of these parallelograms spanned by the vectors u and v. So let's go to our theorem, which this results from. So like before, we want to let u and v be vectors in R3. Then we have this relation that the norm of u cross v all squared is the same as the norm of u all squared times by the norm of v all squared minus u dot v all squared. Okay, so how would we go about proving this? Well, we can just prove it directly by expanding the left-hand side of this formula here, using our definition now of the vector product, and then just arriving at the right-hand side. So maybe I'll just put a short calculation. Shows that, what do we have? We have that the norm of u cross v squared is going to be, we've just seen, that's the norm of u squared times by the norm of v squared times by sine squared of theta. Well, we can write using some trig identities, sine squared as 1 minus cosine squared. So that's the norm of u squared times the norm of v squared times 1 minus cosine squared of theta, which is equal to just expanding this out because these are just real numbers and that clearly distributes. So we have, this is the norm of u all squared, norm of v all squared, minus the norm of u all squared, norm of v all squared, cosine squared of theta. And we realize this thing here, right, is simply just the dot product or the scalar product of u and v all squared. So in other words, we've got the norm of u squared times by the norm of v all squared minus u dot v all squared, which is exactly the area of this parallelogram we've written above, and exactly the expression that we're trying to prove. So that's our proof finished. Okay, so much like we talked about in the with the scalar product, we started talking about properties of the scalar product next. In the next video, we're going to talk about properties of the vector product. So as always, I remind you to read the notes and check all the proofs and check all the examples or anything in there. Read them in detail and attempt any problems in the module handbook pertaining to the material that was discussed in this video. So thanks very much for watching and see you in the next video.